Good morning, good afternoon, good evening, depending on where you are joining us. Welcome to this webinar on building IoT applications in the cloud. My name is Janakiram MSV. I am an architect, analyst, and advisor running my own firm, Janakiram Associates. So in the next 45 minutes to an hour, I'm going to walk you through various steps involved in configuring a real-time IoT application in the cloud. So let's get started. Internet of Things is not actually new. It's been around for quite some time. Back in 2010, we had connected devices. For example, our printer that was connected to the computer over a Wi-Fi, our media player connected to the headset over Bluetooth, and there were other gadgets that were essentially connected to either our mobile phones or to other devices. When we fast forward this trend to 2017, we witness a sort of an explosion when it comes to connected devices. Today, from smart lighting to smart thermostats, to connected cameras, to environmental sensors, personal voice assistants, to wearables, there are Internet of Things and connected devices everywhere. At the front and center of this revolution is the cloud, which essentially enabled us to connect these devices to each other through a centralized location, and of course the ability to acquire data, store it, process it, query it, and analyze it in the cloud. So the rise of cloud and the need for connected devices brought us into the era of Internet of Things. So let's take a closer look at this architecture and what it means to developers. So when you look at the big picture of IoT, it's a three-tier architecture. The first tier is the devices, and the second tier is the IoT platform. Think of that as the middleware for connecting the devices. And then the third tier is the applications tier. The devices tier consists of various devices, both intelligent devices and legacy devices. Intelligent devices can make a connection to the outside world over the internet. Non-intelligent and legacy devices take help of a proxy, which is called as the local gateway. But irrespective of how the devices are connected, they establish a connection with the IoT platform, and their multiple building blocks handle the workflow and take care of the connectivity and processing of various data sets and data streams. The outcome of the IoT platform is consumed and visible through the application tier. For example, the data that is streamed by the devices to the IoT platform is available as a dashboard across your television, web application, mobile, or wearable. At the same time, you can use any of these front-end applications to control one of the devices. For example, it is possible for you to pull out your mobile phone and control a device that is connected to the IoT platform. So that is the big picture. Let's take a closer look at each of these components. As I mentioned earlier, devices are of three types. The first one is the IP-capable device, which can establish connectivity to the IoT platform over internet. It uses higher-end protocols like TCP, HTTP, or WebSockets. Then there are non-IP-capable devices, which use low-power memory-constrained devices, and they cannot establish a connection over TCP or HTTP. So they rely on very lightweight protocols like Zigbee, Bluetooth Low Energy, Z-Wave, or power over Ethernet. Then there are legacy devices that have been a part of manufacturing equipment and automobile industry for a long time, and they rely on legacy technologies like SCADA, RTU, PLC, which is the process logic control or programmable logic control, and of course telemetry. So these are the devices that are essentially connected to the physical equipment or physical switches that we want to operate, and they're also capable of acquiring data through the sensors and sending them to the next stage. So those devices that are not capable of talking to the platform directly, they take help of the gateway. And gateways are of two types. The first one is called the field gateway, which is essentially representing a collection of devices or an array of devices that are not able to establish connectivity to the central cloud or an IoT platform. So the field gateway, which is also called as an IoT edge gateway, is responsible for representing those devices with the cloud platform. The gateway registers each device with unique identifier and maintains a registry, which is almost like an yellow books for all the connected devices. Metadata like the serial number, the make, model, firmware version, all those details are centrally maintained in the device registry, which is managed by the gateway. The gateway also enables M2M, which is machine-to-machine communication, and it is responsible for orchestrating the messages flowing back and forth between devices. So the gateway also handles security, and it authorizes devices when they connect, when they publish and subscribe to messages. Devices can be whitelisted or blacklisted. In case one of the device gets stolen or gets corrupted, it can be very easily blacklisted and it will stop interacting with the centralized platform. Gateways typically expose a set of disparate protocols including HTTP, MQTT, AMQP and WebSockets. More on this later. So that is the second building block. The third building block of an IoT stack is the data ingestion component. Remember, I was mentioning about devices capable of streaming data. So the data ingestion layer is responsible for acquiring the data from tens of thousands and sometimes even millions of devices and passing that stream of data to multiple parties that are subscribed to the data ingestion endpoint. If you are familiar with technologies like Apache Kafka, that is one of the popular open source data ingestion engine. It can ingest millions of data points in a few seconds. It enables one-way communication between devices and platform, and we only connect those devices that are generating data and that needs to be acquired in real time. So those devices typically get connected to the IoT platform via the data ingestion layer. Once the data passes through the ingestion layer, it is going to be stored for further processing. And that's where we use a combination of object storage, NoSQL databases, also the time series databases and relational databases. So the choice of database depends on the use case, but essentially the idea is to store the raw data as well as store the processed data, which is going to be useful in deriving insights. These days, there is also a concept called data lake, which is going to store the data in its raw form. And that is primarily used for tracking and performing audit trails on the incoming data stream. Both the raw data as well as the data that is the outcome of various processes meant for real-time analysis is also stored in the same storage. And that is exposed as a REST API for applications to consume. So this REST API will be used to generate visualizations and dashboards that is useful for decision makers to get insights into the platform or the connected devices. From storage, data typically passes through one of the channels called hot path analytics. This is where we transform, process, query, and analyze streaming data. An example of this is a connected car that is sending the current latitude and longitude. So we are going to acquire the data in real time and call another web service that will transform the latitude longitude data point into a zip code. And in case there is a problem found with the car, it uses that data to guide the driver to the nearest service center. And all this happens in real time. So the data points that go through the real-time stream analysis are also called as complex event processing engine, is actually called as the hot path analytics. This is where you process data points as they come using concepts of sliding window and tumbling window. Data can also be stored and processed over a period of time, and this typically takes place as a batch process, and that is used for deriving historical trends and capturing insights from data that has been processed and maintained over a period of time. For example, the same connected car can send the fuel consumption details every hour, but you can't really make out the fuel efficiency of a car by processing it as it comes. Instead, if we accumulate this data over a period of time and compare it with the number of kilometers that it has traveled, we can derive a correlation between the number of kilometers covered and the fuel consumption, and then arrive at the fuel efficiency index for that car. A company like Uber could actually use that to find out the most efficient, fuel efficient car in their fleet and the least fuel efficient car in the fleet. So data that is captured for long-term processing and historical trends goes through this path, which is called the cold path. So that's the big picture of IoT. And finally comes in the application layer. This is where we use a lot of mobile applications, wearable applications, and even televisions will start having the apps to control these devices. The role of an application layer is of twofold. The first one is to get the user experience in terms of the visualizations, dashboards, and real-time graphs that indicate the current state of the devices. So a lot of operational teams would watch these very busy graphs and slides and dashboards to basically make sense of the current state of the devices. The second role of an application layer is to send commands to the devices. For example, when you want to control a specific switch or an equipment or an actuator, you would do that from an application. So the application tier acts as the front end for both controlling the devices as well as consuming the insights and presenting that in the most intuitive form. So all these are the layers of a typical IoT platform, and this is how an enterprise IoT stack is built from the ground up. Since we are talking about prototyping, obviously we are not building an enterprise IoT stack. I want to give you a sense of what it takes to build a simple end-to-end complete IoT solution. So when we analyze the most essential components of an IoT solution, we have devices at one end of the spectrum, and we have analytics and applications at the other end of the spectrum. So devices are going to generate a lot of data, and we use them from the analytics or the application tier. And application can control any of the devices that are connected to the MQTT broker or to the platform. So the devices that are connected to the platform are actually talking to a centralized orchestration engine called the MQTT broker. And if you recall, this is the gateway plus an M2M orchestration engine, which will facilitate the messaging across multiple devices. It uses a pub-sub model where a device will publish its data to a topic, and any interested party subscribed to the same topic will be able to receive that message. On the other side of the MQTT broker, we have two more subscribers. The first one is the Ingestion Engine, which is responsible for acquiring the data that is entering the MQTT broker. We can configure that to get all the messages or filter on a specific topic and get selective messages. Then we have the Rules Engine, which is also acting as a subscriber to the MQTT broker, and its job is to essentially get the data and check for certain rules or business logic, which will either control the device or will invoke an application based on an alert or a notification. For example, device 1 could be a smart thermostat, device 2 could be an air conditioner. So when the smart thermostat starts publishing the current temperature, it is going to be received by the rules engine, and there could be a simple rule that says if the temperature falls below 20 degrees Celsius, switch on the AC. So that rule is defined in the rules engine, and when the threshold is met or the rule condition evaluates to true, it talks back to the MQTT broker, and MQTT broker sends a message to the air conditioner to turn itself on. So this workflow is managed by the rules engine. At the same time, the thermostat might actually send the ambient room temperature every 1 minute, and that data comes and sits in the Ingestion Engine, which is going to be responsible for feeding multiple other channels One of the channel could be a time series database where we are going to store and analyze the data. The other one could be, for example, a machine learning model which is going to find an anomaly with the thermostat or the air conditioner. It can be anything, but the ingestion engine is a layer that decouples data from rest of the consumers. And finally, the analytics layer is responsible for helping us visualize the aggregated data or the outcome of the processing. So these are the most essential but complete set of building blocks of an IoT solution. So now let's go ahead and map them to a set of open source technologies. So let's start with the devices. I have two Raspberry Pi devices with me. You can actually see them here. So you notice that I have two Raspberry Pis and they are connected to a bunch of sensors and actuators and also bulbs. And these are completely independent. For example, let me get rid of this for a while and show you the first one. So this is a Raspberry Pi which is basically responsible for receiving the data. So I call that as the subscriber. And this has two LEDs connected to it. This is the green LED and the other one is the red LED. So depending on a rule or depending on a condition, we'll turn on and turn off these LEDs. So this is one of the Raspberry Pis and that is completely independent. It is connected to a power bank and it can participate in the solution. So let's get this out of the frame and let's look at the other one. So the actual Raspberry Pi that you see here is the publisher and it has two components. There is a switch, right? And then there is a sensor which is called the DHT11. So DHT11 is responsible for streaming the temperature and humidity via Raspberry Pi. So this sensor is connected to the Raspberry Pi and the button is also actually like a sensor, but it is more analog. So it either sends a 0 or 1 based on the state. So now throughout this demo, we'll use one of the Raspberry Pis. Actually, this Raspberry Pi is going to act as a publisher because it is generating the data or sending the signal. Then the other Raspberry Pi that we have here is going to act as the subscriber. So let me turn this around and show you the LEDs. So we have a couple of LEDs. It's a bit cluttered, but that's the best I can ensure to show you the entire setup here, right? So these are the two bulbs connected to the Raspberry Pi which is acting as a subscriber. So those are the devices. Now those two devices are connected to an open source MQTT broker called Mosca. Mosca is written in Node.js and a wonderful developer called Matteo has built it. It is available on GitHub and it's also packaged as a Docker image. So we use Mosca as the MQTT broker for connecting our Raspberry Pis acting as publisher and subscriber. The messages that are flowing into Mosca are consumed by another open source ingestion engine called Telegraph. As I mentioned earlier, Telegraph acts as the ingestion engine, which means as the data enters Telegraph, it can flow into multiple channels. And in our case, to keep this simple, we are storing that in a time series database, again an open source software called InfluxDB, which is a time series database. And the output of InfluxDB is going to a dashboard, a visualization front end called Chronograph. So Chronograph is a very powerful dashboarding tool that can grab the data from InfluxDB and helps us visualize that. So that is the analytics path. Now let's consider that as the data processing, analytics, ETL, whatever you want to call. Then we have the rules engine in the form of Node-RED, which is very powerful. And you can use JavaScript to basically create simple rules. And you can route the data as it enters the Node-RED engine. And this can invoke third-party applications or can even send commands back to one of the devices. So that is the setup that we have. Walking you through the architecture a little bit. So we are using what is called as the tick stack: Telegraph, InfluxDB, Chronograph, and Capacitor. In this demo, we don't use Capacitor, which is basically an alerting ETL tool for finding anomalies in time series data. We don't need that for our demo, but we are using Telegraph, InfluxDB, and Chronograph. So the TIC of tick stack is being effectively used in this demo. As I mentioned, this is Node-RED, which will give you a canvas where you can draw a flowchart like workflow, and excuse me, as the data flows, you can basically control either the messages that are flowing back to the devices or invoke third-party applications. In our demo, we're going to see how we can send some messages to Twitter. So basically, when the temperature goes up, we are going to send a tweet, and you can monitor your Twitter account to find how your thermostat is functioning. So it's going to be a fun demo. So the steps involved are pretty straightforward. We start by launching a droplet in DigitalOcean. And since we are using containers for most of these components, we install and configure the latest version of Docker. And then we pull appropriate Docker images, including Mosca, Telegraph, InfluxDB, Chronograph, and Node-RED. After that, we go ahead and connect the devices to Mosca, which is the MQTT Broker. And we immediately start visualizing the data in Chronograph to ensure that the data is flowing into the system. And after verifying that, we'll go ahead and configure the rules in Node-RED. There are a couple of disclaimers that I want to make. Though this solution is complete, it is not production ready. To keep this simple, we are not configuring security, but it is completely possible for you to secure this end-to-end. For example, you can implement SSL, you can implement TSL, you can put this behind a firewall and a load balancer and scale it out, at the same time securing the ports and authenticating and authorizing your devices. But the objective of this tutorial is not to show you the security aspect of IoT, but the core building blocks of an IoT solution. So we are conveniently leaving aside the security aspect. So the disclaimer is this demo is not production ready. So if you are planning to connect your production devices or build a live application, you got to do many other tweaks to ensure this is production ready. So with that disclaimer, it's time for us to go ahead and configure an open source IoT stack on DigitalOcean. So let me start by showing you the setup that I have here. So the very first step is to launch a droplet in DigitalOcean. So I have gone ahead and configured what is called as the Thing server, which is my VM or the droplet running in Bangalore. And this is going to be our server to host the IoT stack. So the first step is to grab the IP address and SSH into this box. So to keep this short, I have already configured Docker. So we see that we have the latest version of Docker. With that in place, I also want to show you my devices. So I'm going to log into the publisher. This is my first Raspberry Pi, which is going to act as the publisher, the one with connected sensors and a switch. So this is running Linux on the Raspberry Pi. It's running on ARM architecture, ARM v7. Let's also log in to the other. Okay, this is my publisher, which is already logged in. Let me now log in into my subscriber. So SSH Pi followed by sub. So this is going to get us into the device, and this is my subscriber. And obviously this is also running a flavor of Linux. So now we have two devices, a Raspberry Pi acting as a publisher, another one acting as a subscriber, and we have a centralized server. So we have the infrastructure in place. Let's go ahead and build the stack. So the very first step is to build some, create some directories. So I'm first going to make a directory called IoT, and this is where we're going to store some data files. So they are essential for the containers when we eventually launch them. So I'm going to create a few directories that are essential for our containers to get the mount points. So now we have 3 directories for InfluxDB, Mosca, and Telegraph. We don't need a directory for Node-RED because we are not going to store anything there. After that, I go ahead and create a Docker network. This is a very important step because all the containers that we're going to launch are connected to the same overlay network, which is the shared network for all the containers. So I go ahead and create this network. So when we do Docker network ls, we see that there is a network that we just created, an overlay network called IoT. Excellent. So now we are on our way to the next step, which is launching the broker, which is the MQTT broker. So the Docker run command is very familiar, except that I am associating this container with the IoT overlay network, and we are exposing port 1883 and port 8080. So port 1883 is basically the MQTT standard port, and this is the HTTP port. So data can be sent to this broker via either port 80, which is HTTP, or via 1883, which is MQTT. And we are mounting the DB directory inside the container as /DB. So let's pull this image and run it. So this is going to take just a few seconds, and very soon we will have the Mosca container up and running, which is going to be our core MQTT broker. Okay, it's picking up speed, and hopefully we'll be done with this very soon. I couldn't cache these containers because I just launched a droplet. So bear with me as I show you downloading these images. All right, so now we have the Mosca container up and running. So we see that it is now available on these ports. So with the MQTT broker in place, time to connect our devices. So the first thing that I'm going to do is to go to my Raspberry Pi acting as the publisher, and this is connected to the internet via the built-in Wi-Fi. So Raspberry Pi 3 comes with built-in Wi-Fi, Bluetooth, and Ethernet. So I'm actually using Wi-Fi to connect to DigitalOcean's droplet. So I have a directory which is called DigitalOcean, and here I have a couple of Python scripts. The first script is the button.py. So let me show you the code. So this is a standard Python script. It uses PAHO MQTT library, which is the standard way of connecting to an MQTT broker. So I grab the MQTT host via the command line arguments, which means when I'm running this, I'm going to pass the public IP address of the droplet, and this is tracking the state of the button in a loop. So every time the button state becomes 1, it sends the value on, and every time the button state becomes 0, it sends another JSON payload with value off. So pretty straightforward. So now all we got to do is to launch this with the IP address of our droplet so that it can register with the MQTT broker. So now immediately it starts sending 1. So that's because if you actually see the button here, it is in an on position. So I'm going to turn it off, and guess what? It becomes 0. So that means the state is being sent to the device or the MQTT broker. And now what we're going to do is to launch the bulb. Sorry, I need to be in the right directory. So I launch the bulb.py here, and bulb.py acts as a subscriber. So the idea is to control the bulb remotely from this button. So this is where the exact opposite of the publishing process takes place. So it subscribes to a topic, which is called the button 1, and it grabs the payload Based on the value, it will turn the LED either on or off. And the LED is connected to pin number 4. So pretty straightforward. And now let's go ahead and launch the bulb. And for this, we need to pass the IP address of our droplet. Okay. So now the bulb is going to be controlled from the button. So let's give it a shot. So now you actually see there is a bulb, and here is the button. When I turn this on, the red bulb glows, and when I turn this off, it goes off. This could be a very simple demo, but it does convey a very powerful scenario where we are actually connecting these devices to the cloud. So even though these Raspberry Pis are sitting next to each other, they don't know that they are on the same network. Actually, every message sent from this button is flowing to the Bangalore data center where DigitalOcean is hosted, and it is talking to our droplet, and the droplet, which is running the MQTT broker, will route the message to our subscriber to turn on or turn off the bulb. So that means one Raspberry Pi can be in New York, the other Raspberry Pi could be in Bangalore, and I can still control this bulb from the same button as if they are connected to each other, or as if they are next to each other. So that's the beauty. So this is also a validation of our MQTT broker's configuration. So far so good. Everything looks the way I wanted it to be. Perfect. So let's stop these two. And I want to show you the next piece of code, which is the sensor. So remember, I actually showed you that there is a sensor attached to one of our Raspberry Pis acting as the publisher, and this is streaming the humidity and temperature. So we'll leave this as it is, come back and take a look at this code. So this code basically grabs the data from the sensor and publishes that to Mosca using a specific format. So it is publishing to a topic called environment, and it sends the live temperature. So we are grabbing the temperature from the sensor, converting that into a string, and we are adding some metadata like building 1, which is actually called as a tag. So we'll publish this information. But before we publish this, we want to make sure that our storage and our time series database is in place. So it's time for us to take our demo to the next level. So what is that step? We need to now run the time series database. So let's go ahead and run this. It's going to pull the InfluxDB image from the Docker Hub, and we are going to have the time series database up and running in just a few minutes, actually seconds. Fortunately, the network is fast enough, so we should have InfluxDB up and running in no time. And there we go. So now when I do a Docker PS, we see that the InfluxDB container is also up and running. So before I start ingesting the data to it, I need to initialize it. So how do I initialize? I launch another container to access the CLI and talk to the InfluxDB database. So now I'm actually launching another container, and notice the --rm. This is basically a switch that says finish your job and immediately remove the container. So I'm using that, and this drops us right into the InfluxDB shell. And here I'm going to create a database called environment. So this database is going to be the container for our time series database. So now I'm going to use this database called environment, and we'll go ahead and insert a couple of sample records. So the first one that I'm inserting is the collection called temperature. Metadata is building 1, which is a key value pair, and the value of this measurement is 29.2. So I'll also go ahead and put another data point, one more. Okay, and that's it. So now we initialize the database and populated it with some sample data. So, and we are done with that container because we don't need it anymore. Excellent. So now that we have this in place, let's go ahead and query the REST endpoint of InfluxDB. So InfluxDB is listening on port 8086, and if we actually hit that endpoint, we'll see a JSON payload, and the values are basically what we entered in the last step: 29.2, 31.1 and 33.3. So this represents the temperature that we entered into our sample data set. Excellent. So now we have the time series database in place and the broker, MQTT broker, in place. So it's time for us to go ahead and connect the MQTT broker with the time series database. But how do we do that? Well, before that, we need to configure Telegraph. So we are going to create a file called telegraph.conf, and telegraph.conf is the glue between the MQTT broker and InfluxDB. So this is where we basically pipe the output of Mosca as an input to InfluxDB. So this is the configuration file. If you carefully notice, there is an output which is InfluxDB, and we are basically telling Telegraph to use this URL. And because InfluxDB and Mosca are sharing the same network, overlay network, Telegraph can very easily discover these containers by name. So InfluxDB will be resolved because they're connected to the same network segment. So environment is the database name, precision is seconds, and there is a timeout that happens at 5 seconds. The input is coming from MQTT, so we are configuring Mosca, which is the container name, and we are saying subscribe to environment topic, which is where our Raspberry Pi is going to publish the data. Influx is the format in which the data is coming, so it is basically the collection, which is temperature, followed by a key value pair, which is building 1, and then the live temperature. So let's grab this and create a configuration file. So that is it. So now we have a configuration file in place, and with that in place, we can go ahead and launch the Telegraph container. And if you notice what I'm actually doing, I'm mapping the conf file to the conf file inside the container in a read-only mode. This will initialize Telegraph as it comes up, and it instructs Telegraph to take the input from MQTT and feed the output to InfluxDB. So let's go ahead and launch this. This is going to take a minute to pull from Docker Hub, and very soon we'll have this as an intermediary between Mosca and InfluxDB. Excellent. So that is it. Now we have 3 containers: the Mosca MQTT broker, InfluxDB for time series database, Telegraph as the Ingestion Engine. Excellent. So with that in place, our next step is to launch the dashboarding tool, which is called the Chronograph. And Chronograph is listening on port 10,000. So let me launch this. And Chronograph is a standalone utility which is going to help us visualize the data. So let's give it another minute, and it's going to pull the container, and we'll be able to visualize the streaming data. Fantastic. So now we have almost everything in place. This is Chronograph listening on port 10,000. So we have all the 3 containers in place, actually 4 containers with Chronograph coming in. So let's go ahead and start streaming the temperature data. So I'm going to call the sensor.py with the IP address of our droplet. So this is going to start sending us the temperature, the humidity, and the electricity consumption. This is actually simulated data which I use for some other purpose, but we are only interested in the temperature. So currently it is midsummer in India, and you see my room is very hot. I switched off the AC to avoid the noise. It's 32 degrees out here, which is pretty hot. All right, so now that this is coming in, let's go back and check the logs. So now I'm going to do docker logs followed by telegraph. And this tells us that the agent is configured and the MQTT client is connected. So this is an indication that telegraph is able to mediate the data flow between Mosca and InfluxDB. Perfect. So with that in place, let's switch to another browser, and I'm going to hit port 10,000 on our droplet, and that immediately shows us the InfluxDB configuration of chronograph. So we are going to add a new server. Let's call this DigitalOcean, and the host is the IP address of the droplet, and that's it. So now we have successfully added our droplet to chronograph. Let me click on done, and then we're going to add a visualization. Let's call this temperature. So what we're going to do now is to pull the live data coming from our sensor into our dashboard, coming via InfluxDB. So I click on this. The server is already configured to be DigitalOcean, and the database is environment, which we created previously. This is optional, but I'll select AutoGen and apply. So now I'm going to select the building, and this is going to be, okay, first I need to configure temperature. Building is going to be 1, and it immediately picks up the data from there. Fantastic. Okay, so now this actually shows it started from 29.2, went all the way up to 33, and then it has also touched 33 and again falling down. So this is a live graph, and I can set the refresh window to 5 seconds where it automatically starts refreshing the dashboard. Now let's click on done and create a dashboard. So this dashboard will give us a better experience of what we configured. All right, so let me save this, add an existing visualization. So this is the one that we created earlier, add visualization to the dashboard, and there we go. So this is our live chart for tracking the temperature. So currently, if you notice, it is hovering between 33 and 32. So let's leave this as is. The good news is we have our data pipeline created. It's not a very sophisticated pipeline, but nevertheless, we have Ingestion Engine, we have a time series database, and we have a front end to visualize data. Excellent. So with that in place, let's now go ahead and configure the rules engine, which is Node-RED. So what do we do? So it's yet another container. So we launch the Node-RED container, and that's going to listen on port 8080, again connected to the same overlay network called IoT. So this is going to be a slightly larger image. I'm not pulling the slim version of it, but it should be done pretty quick. And we have the most exciting part of the demo coming up. All right, so now once this gets launched, we will access Node-RED from the browser and create a couple of rules. The first rule that I'm going to create is to control the color of the bulb based on the temperature. The second rule that we'll configure is to tweet when the temperature goes beyond a specific threshold. So now let's check if we have all the containers. There we go. So Node-RED is also up and running. Fantastic. So let me switch to the browser, grab this URL and access port 1080. Oops, this is not 1080. It must be 1880. Excellent. Okay, so this is the canvas that I was talking about. So now that we have Node-RED in place, the very first step is to connect Node-RED as a subscriber to our MQTT broker, which is Mosca. So let's go ahead and configure. So I click on add new broker, and we need the IP address of our droplet. The port is 1883. We are not changing anything here. So let me click on add, and the topic that we are going to listen on is called environment. and let's call this the sensor. Okay, so now the sensor is configured, and if I click on deploy, but before I do that, let me okay, I made a silly mistake. So instead of the input, I actually configured the output, but that's fine. So let's leave this aside, and I'm going to use this for the bulb. So if this is representing the bulb, I need a sensor, and that's going to be the input. So what we'll do here is drag and drop another MQTT node and associate this with the environment topic. So now the input comes, or rather let me call this the sensor, published subscribing to the topic called environment, and this is the topic that our temperature sensor is streaming the data into. So let's connect this to the payload, which is the debug node, which will show us the output, and click on deploy. So if this is successful, we should start seeing the output. So okay, so the MQTT node is connected. Let me make sure that we are still, there we go. So my Python script crashed for some reason, so never mind, we'll launch this again, and we should start seeing that in our debug window. Excellent. So now we have the data flowing into Node-RED, and we can do a lot of wonders. So let's detach this. What we are interested now is to extract only the value and nothing else. So we are not bothered about the temperature, building one, and so on. So for that, what we'll actually do is to create a custom function. It's almost like a pipeline. So let's call this as parse. And here I'm going to copy paste a few lines of code where we use JavaScript to extract the value of temperature. So we'll split the incoming string twice to make sure that we are able to grab the temperature alone. So now we'll connect the output of the parse node, click on deploy, and from now we'll only see the actual temperature. That's all we are interested in, and the message payload is just the number. Excellent. So now that we have the data coming in into one of the nodes, we can start creating the first rule, which is to turn on and turn off the bulb, or change the color of the bulb. So let's call this the bulb rule, and I have a tiny code snippet to basically change the color of the bulb. So here I parse the incoming data, because message.payload sometimes might be considered as a string depending on how I'm sending. I'm actually sending an integer, so this is not required, but to be on safe side, I convert this to an integer, and then if the temperature is more than 30 degrees, I set the color of the bulb to red, otherwise it becomes green. All right, so now I connect the output of parse to this bulb, and let's check if we are seeing that in the output window. So now, since the temperature is more than 30 degrees, we are hovering between 31 and 33, we are seeing the output as red. So I can now take this output and actually connect it to the bulb. So now what happens is, when the actual data flows into it, the bulb starts responding. So we are now taking the data and applying a logic, applying a rule, and trying to control the bulb. So now, if you actually look at this, we are, of course, the bulb is red, and that's what it has been. So let's actually reverse the logic, right? So now what I'm going to do is, I'll change this to, let's say, if it is only more than 35, I want this to be red, otherwise it is green, and I will go ahead and deploy. So now, when we actually come to the, okay, so another small mistake. So now we need to actually launch the subscriber. So now the subscriber is up and running, and we see that the bulb is changing its color, right? Not convinced? Well, let's go back and reset the rule. So we'll turn this to 30, right? So done, deploy, and we are back to red. One more time, right? So let's increase the threshold to 35 degrees, hit deploy, and the bulb has switched to green. Fantastic. So this is working the way I wanted it to. That's not all. We can do something more interesting. So how about tweeting the temperature, right? So we can define certain threshold and we can start tweeting. So let's create a new rule. Call this as tweet rule. And the idea is to actually send the payload to Twitter. So again, we have a very simple JavaScript code snippet. If the temperature is more than 45, because I don't want to tweet every time the temperature is touching like 35, which is very common. So only when it touches a very high-end threshold like 45, I want to go ahead and send a tweet. So I will deploy this and feed the output of parse. So we are converting the temperature to a numerical value and sending it to the tweet rule. And then we'll check what the output is going to be. So when I click on deploy, this will start showing us, of course, the threshold is still very high. So let's turn this to 30. And now when I actually deploy, we'll see that it is generating a text that says temperature is high at 32 degrees Celsius and the timestamp, which is in UTC. So we are now all set to basically go ahead and push this to Twitter. So fortunately, Node-RED gives us a Twitter output, right? So here is the node where you can send the tweet directly from Node-RED. So we'll connect this, and I need to configure Twitter. So here I go ahead and authenticate with one of my demo accounts. That is done. Add, and we are all set to go. So now with every tweet, we'll actually see that. So now it's time for me to show you my wonderful bot, which is an automated Twitter account. And here, if you notice, we are seeing, I deliberately called this Johnny Robo, and I took the screenshot from one of the popular movies in South India to symbolically show that it is actually a robo. So now we can actually see that we are seeing the output of our sensor data in Twitter with just a few lines of code. And this is visible right here. So you're actually noticing that it is tweeting in real time. And when the bulb rule changes, the bulb also functions. So this is an end-to-end demo. So let me remove this before Twitter blocks my account. I'm tweeting too often. So now that we have the complete workflow in place, you can actually use this to either control the device, that is basically turning on and turning off the bulb or changing the color, or even talking to a third-party application like Twitter. So this is a very powerful way of building IoT applications. And by the way, let's take a look at our dashboard. And this is very cool. So we are actually seeing that the data is, hovering between multiple values, and it gives us a pretty cool visualization of the temperature data. So that is the demo that I wanted to show. Time for me to take you back to my slide deck and do a quick recap. So what we just saw, it is basically two devices connected to the MQTT Broker in the cloud, configured as Mosca. The output is captured, or rather subscribed, by Node-RED and Telegraph. The data is passing to InfluxDB, from where we are visualizing the data through a chronograph dashboard. Node-RED is used as the rules engine for us to configure powerful rules to control the devices or to talk to third-party applications. So this was an end-to-end walkthrough. Thanks for watching. We appreciate your time. Thanks for attending and joining us for this series. This is Janakiram signing off. Thank you.